Well, Year 12. Today we're going to be looking at the first of the new Year 13 mechanisms, which is one called Nucleophilic Addition, and we're looking at two different reactions. We're looking at the reduction of carbonyl compounds and the reaction of carbonyl compounds with cyanide ions. So this is a really, really important reaction in chemistry, used all over the place to produce all sorts of different molecules. So it's a really, really key reaction. So we're going to start with sort of the simplest version of this, which is going to be, we're going to take some got methanol here, and we're going to react it with sodium borohydride, NaBH4. So this is commonly referred to as sodium borohydride. That's not actually its systematic name, its IUPAC name. Its systematic name is horrendous. It's sodium tetrahydridoborate. So it's usually called sodium borohydride or just NaBH4. So we're going to react these two together. Now the sort of general reaction scheme is what we're going to do. This is going to do a reduction of the molecule. So we're going to add H2 across the double bond to form the alcohol. So this isn't it. This is the overall what we're going to form. It's going to form the alcohol. So we've added these two hydrogens to the molecule. So we've added these two. So it's equivalent of adding H2s, which we call a reduction. So this is sort of the start and end point. We need to be able to do the mechanism for this. So we're going to run through that mechanism. So the first thing to note is that we're not going to actually represent NaBH4 as NaBH4 in the mechanism. We're going to represent NaBH4 as an H- ion or a hydride ion. Now this is not present in the solution. So this reaction is done in water. It's done in water as a solvent. Now the NaBH4 actually slowly reacts with the water, so you have to do it reasonably quickly, but it's quite a slow reaction. The reaction between these two produces hydrogen, but it takes like half an hour or an hour for them to react. So you've got time to go ahead and do the desired reaction, which is with the methanol in this case. If H- were present, it would essentially blow up. So if you take sodium hydride, so NaH, so that is essentially an Na positive and an H-. So that hydride ion is present. If you put that with water, it would blow up in your face. The H- ions are incredibly reactive, very, very unstable. The Na plus is not an issue. When you put table salt, NaCl, that doesn't blow up. It's the H- that's highly reactive. So H- is not actually present, but we're going to use H- because it kind of behaves like there is H-, and it makes the mechanism simpler. If any of you do university chemistry, you will very quickly come across the let's say the more proper mechanism where we do use the structure of NaBH4, but we're just going to represent H-. So we've then got our methanol that it's going to react with. Now we need to think about which where is that H- going to be attracted towards in this molecule. So if we consider the polarity, C's and the H's, very little difference in electronegativity between the two of those, but the C and the O, we're going to have difference in polarity here. So we're going to have a delta plus and a delta negative. And so the lone pair from the H-, making sure I'm showing my lone pair, will be donated towards the carbon. Now for that carbon to accept that pair of electrons, if it did that, it would give it 5 bonds. It would go over the 8 in the valence shell for carbon. So we have to break a bond. Now the CH bonds are quite strong, and if we put the electrons from the bond onto the hydrogen, it just forms an H-, so forming very, very high energy things. So that's very difficult to do. But the double bond between the carbon and the oxygen is not, I think it's a little bit weaker than a CH bond, so it's a little easier to break, and it's going to put electrons onto an electronegative atom. So it's going to form a reasonably stable oxygen negative, because we're putting electrons onto an electronegative atom. So the product of this step So we've got our O negative, and then we've got the 3 C's now attached onto 3 hydrogens attached onto the carbon. So this is then sort of in solution. It's then going to we then have to follow up this reaction with an acidic workup. So we're going to add a small amount of acid into it. So we're going to, after the first stage is sodium borohydride, followed by, say, a small amount of HCl, aqueous HCl. So a small amount of aqueous HCl afterwards. You don't put those together, they probably catch fire. So you let this react to form this intermediate, and then later on you add the acid. So that acid, that's a source of H plus ions. So we've got some H plus ions. So lone pair from the oxygen towards the hydrogen. Forms the OH bond, and we formed our alcohol. So we can reduce the aldehydes or ketones to their respective aldehyde. So just some other examples, if we take butanone, that will be reduced by NaBH4, that will form butan 2-ol. This won't work with carboxylic acids, so it won't reduce a carboxylic acid. So that will not react to form, I don't know, something like okay, that won't happen, that doesn't work. So what will happen in this case is the acidic hydrogen here, we've got the acidic H, I just draw the bond on, you've got your H minus, so it would just react with the hydrogen, so it would just react to the base rather than acting as a nucleophile, which is what it's doing here. It'll act as a base, it will just take the hydrogen off of it, so you would form H2 gas and the carboxylate ion. And if it generates enough heat to set fire to the hydrogen gas, you've got an explosion on your hands, or at least a fire. So this is why you need to be careful with these kind of things. So the other reaction is between the carbonyl and a cyanide ion. So if we take, let's take some propanone, or commonly called acetone, and we'll react that with some potassium cyanide. This is going to form something called a hydroxynitrile. So this cyanide group, when it's part of part of the carbon chain, we call it a nitrile, and then we've got OH as a side group, and when it's not the primary group, we call it a hydroxy. So this is a hydroxynitrile. Now the mechanism for this, we're going to need, our reagents. We need KCN, and we need to follow that up with some acid as well. So you'd want to add some aqueous acid in a second step as well, similar to the last one. But our mechanism is the same mechanism. It is nucleophilic addition, but we just got a different nucleophile. So in this one, the lone pair on the carbon, not the lone pair on the nitrogen, attacks the carbon. We break the double bond, and we put the electrons onto the oxygen. This forms this intermediate, which would be stable under alkaline conditions, which it would be what's formed when you just add the KCN. But we're then going to we'll add some acid So we'll add some aqueous hydrochloric acid, fairly dilute. That's a source of H+ ions. So lone pair on the oxygen donates electrons towards the H+, and that forms our product over there. So those are the two mechanisms. What we've left out is the difficult part of this one, which is the stereochemistry of the reaction. So this is where we're adding a sort of extra layer of complexity onto the reactions that we've seen in year 12. And so this is why we covered enantiomers in our previous lesson, because we have to look at the optical isomerism or the stereochemistry of this reaction. Okay, so I've got here a carbonyl, which I've made using the molecular models. And we're going to look at the reaction in a 3D perspective to see the